Hello students, welcome to EPG Pathshala. I am Devapriya Chaudhary from JNU, and today we are going to talk about molecular modeling under the paper Computational Biology. So what is molecular modeling? Molecular modeling is the science which attempts to understand various biological and chemical phenomena in terms of the properties of the constituent atoms and molecules. It provides a link between the living world of biology and the inanimate world of chemistry and physics. Molecular modeling attempts to understand the structure and properties of atoms and molecules on the basis of universal physical laws. It has often been used to predict the structure and properties of molecules and thereby explain various biological phenomena. Of course, it finds immense practical use, particularly in the fields of materials research, drug discovery, and so many other areas. So, let's talk about the techniques of molecular modeling. This can be broadly divided into two groups. On one hand, you have the classical mechanics methods. On the other hand, you have the quantum mechanics methods. In case of the classical mechanics methods, you consider a molecule rather crudely. You consider an atom like a spherical ball, and you consider the bond something just like a spring. In case of quantum mechanics, on the other hand, the basic approach is that you consider the probability of an electron being at a certain place, and you do not actually have an explicit position of either the atoms or the bonds or anything. Now, quantum mechanical methods can be broadly divided into two groups. They are the so-called semi-empirical methods and the so-called ab initio methods. Now, in case of the semi-empirical methods, the calculations, they involve a lot of parameterizations, and the parameters are taken from experimental data. On the other hand, the ab initio methods are theoretically pure in the sense that very little help is taken from experimental measurements. Finally, which method to use? Should we use classical mechanics methods or should we use quantum mechanics methods? The answer lies in the computational power that you require. The classical methods are rather crude, but they operate for very large systems, for your proteins, your nucleic acids, with hundreds or thousands of atoms. You can apply the classical mechanics methods. The quantum methods, by their very nature, to do any calculations with them, you require a lot of computational power. You can use the semi-empirical methods for moderately large systems, say about 100 or even 200, 300 atoms. But the ab initio methods, which are really extremely theoretically pure, does not make any assumptions, etc., but require huge computational power. And so only very small systems with few atoms, maybe in tens, not even hundreds, that's what one can study using ab initio methods. So one of the first things that one would require for molecular modeling is a method to represent a molecule which is understandable to a computer. And whether you are using classical mechanics or whether you're using quantum mechanics, you are going to need some sort of a representation. Now, there are various different ways of representing a molecule for a computer. The simplest one, as you can think of out here, is what we would call the external coordinate representation. Basically, it involves setting up a XYZ coordinate system and setting each atom, which is now considered to be just a point in space, just three coordinates, x, y, and z. So if every atom has three coordinates to specify it, so if there are n atoms in a molecule, we would have required 3n different independent parameters to describe the molecule. Now, there are other ways to do so also. Say, for example, I can take a molecule and I can specify all its bond lengths, all the bond angles, and something called the torsional angle. I'll come to it in a minute. Now, a collection of bond lengths, bond angles, and the torsional angles would completely specify the molecule. However, in this case, you need only 3n minus 6 parameters if you have n atoms in the molecule, which means there are 6 missing parameters. Now, what are they? These are the parameters which specify the absolute positioning and the orientation of the molecule in space. Now, if a molecule is here or a molecule is there, for some purposes, it's the same molecule. So a benzene which is sitting right in front of me, or a benzene is sitting in your room, after all is a benzene, right? So we do not really bother in many cases when about this parameters on the absolute positioning and orientation. So in such cases, 3n minus 6 parameters suffice. Although I must say that if we are looking at, let's say, the interactions between two molecules, right? In such situations, all the 3n parameters for each molecule will be required. So you cannot ignore those 6 parameters. So comparing the two things, external coordinates and internal coordinates, external coordinates require 3n parameters, okay? Internal coordinates require just 6 less, 3n minus 6. In case of external coordinates, the coordinates are very sensitive to any change in the position of the molecule. If I take the molecule here, move it over here, without changing its conformation, in that case also the external coordinates will change. This may be good sometimes and it may not be good sometimes. Internal coordinates, on the other hand, will not change unless there is a change of conformation or configuration of the molecule. So if specifically you are interested in conformational or configurational changes, whatever you are interested, in such cases, sometimes internal parameters, internal coordinates might be advantageous. However, if you are studying like more than one molecule in space and the way they interact, then sometimes external coordinates are better, because internal coordinates will only specify what is internal to the molecule. It will not specify the relationship between one molecule and another molecule. Now let's see whether these two representations, the external and the internal, are they equivalent or not. Okay, that means given a set of external coordinates, can we calculate the internal coordinates? Given a set of internal coordinates, can we calculate the external coordinates? If we can, then it means that these two representations are absolutely equivalent. Now let's take the bond length. Now in external coordinates, for every bond length I have two atoms and I have coordinates. Let's call them x1, y1, z1 and x2, y2, z2. The bond length in this case is nothing but the distance separating these two atoms, and what I have out there is the Euclidean distance formula. You can apply that and you can get the bond length, which means as far as the bond length is concerned, given a set of external coordinates, you can always calculate all the bond lengths. Now let's take the bond angles. Again, given three atoms which are connected, I can define each of these bonds using some vectors A and vector B. In that case, the angle, the bond angle in our case, is nothing but the angle between these two vectors and is given by the inverse cosine of the dot product of these two vectors. Now the dot product, as many of you know, is rather simple to calculate. So, and finding out the inverse cosine is also fairly easy. So given the external coordinates specified in terms of x1, y1, z1, x2, y2, z2, x3, y3, z3, in this case one can calculate the two vectors, and from the two vectors one can obtain the bond angle, which means again in this particular case external coordinates can be completely converted into the relevant bond angles, no problems there. Now let's come to the torsional angles. Here the situation is a little bit more complex, so let me define this. What exactly is a torsional angle? Now to understand a torsional angle, we have to think about it. What we need are four atoms which are connected in a chain. Now given any three atoms in space, a plane is defined. So suppose I have the four atoms A, B, C and D. Atom A, B and C will define a plane. Similarly, atom B, C and D will also define another plane. Now these two planes, they may be coplanar, that is both of them may be embedded in another bigger plane, or they need not be. If they are not, then there is a certain angle between the two planes, and this angle is the torsional angle. Now this also can be calculated given the external coordinates. Just like in case of the bond angles, we can go ahead like this. So given these four atoms, let's define three vectors A, B and C as given in the figure, and then we define three other vectors QA, QB and QC. QA is the cross product of vector A and B, which means QA is perpendicular to the plane defined by atom A, B and C. Similarly, QB is the cross product of vector C and vector B, which means that QB is the perpendicular to the plane defined by atoms B, C and D. And then the QC is the cross product of QA and QB, which means it's the perpendicular to the both of these two perpendiculars. Given such a set of these vectors once we define, I can calculate the torsion angle by the formula which is given, okay, which is the inverse cosine of QA and QB multiplied by the dot product of the vector B and the vector QC. A little bit of geometry will tell you that the dot product of the vector B and the vector QC can have only two values, +1 or -1. So effectively what gives you is the sine of the torsion angle. So there being only 3n minus 6 internal parameters, one thing is clear, that if I go from external to internal, which is 3n to 3n minus 6, I can definitely do it. I have all the information required. But if I have to move from internal to external, 6 parameters I'll have to give. Now for a single molecule, these 6 parameters can be arbitrary. But if there are more than one molecule is there and one has to define the position of one with respect to the other, then we'll have to use that information to obtain the remaining 6 parameters. But be that as it may, there exist very standard general algorithms which always works to convert these 3n minus 6 parameters in internal coordinates to the corresponding external coordinates. There are quite a number of such algorithms. Perhaps the most well known is something what we call the fourth atom fixing algorithm. It has a cleanly analytical solution, but I think in the interest of keeping this talk rather simple, I will just name the algorithm, but I will not describe it. One of the things, external coordinates can be converted to internal coordinates, but in doing so, one information is lost, that is the absolute position and orientation is lost. In some applications, particularly when you are considering just a single molecule, this loss is unimportant. In some other applications, this loss is important, and then we might just have to use external coordinates. But nevertheless, given a situation, sometimes internal coordinates are easier to handle, so we use them. Sometimes external coordinates are easier to handle, so we use them. So one can freely move from one to the other, okay, depending upon whatever we really want to do. Now, given this representation, given these coordinates, what can we do with it? Now, one of the things that we do is that we can calculate an energy, a molecular energy, so to speak, and given different conformations of the molecule, there are different associated energy values, and there is this, let's say, the fundamental belief, the fundamental dogma in molecular biophysics, which states that that conformation of a molecule which is associated with the lowest value of the energy, of the molecular energy, happens to be the most stable conformation and most often is also the functionally active conformation. So much of the time, molecular modeling becomes a process of finding out the lowest energy conformation and then interpreting the properties of that conformation which gives the lowest energy in terms of whatever biological or chemical functions that you are interested in. And much of molecular modeling science is essentially the art of finding the lowest energy conformation. Now again, how is this calculated? So there are two approaches: quantum mechanics, which is very accurate but very difficult to do, needs a lot of computational resources, and molecular mechanics, not very accurate but easier and therefore applicable to large systems. This is just one formula, which is just one of the many different ways to calculate molecular energy. But since you have a detailed separate module on the calculations of this energy, I'm just showing it out here for the sake of completion, and I'll leave it at that. Okay. Now let's look at an application, and the application I choose is finding out the conformational variation, the conformational variability inherent in peptides and proteins. I should preface my talk out here that the reason I chose this, that much of whatever we know about the understanding of the conformational space of peptides is due to the work of Professor G.N. Ramachandran at that point of time in the University of Madras and later on in the Indian Institute of Science, Bangalore. And this is work done completely by Indians and in India. So it's one of the proudest things that we have. Now let us look at a peptide as it is shown there at the top of the figure. Now, the backbone of the peptide, just the N, C alpha, C prime, N, C alpha, C prime, this series. If you look at this, there are 3 torsion angles which define it for every residue. Now, between the single bond between N and C alpha, so that defines a particular torsion angle, we'll call it phi torsion angle. The single bond between the C alpha atom and the carbonyl carbon atom, the C atom, we will call it the psi torsion angle. And the one from the carbonyl to the nitrogen atom of the next amino acid, we will call it the omega torsion angle. Now, if you look at this peptide backbone, the conformation of the peptide backbone will be defined, of course, by its bond lengths, by its bond angles, and by these 3 torsion angles for every residue. Now, chemistry would suggest that the bond lengths and bond angles are generally rather restricted to certain specified value. But the torsion angles, these being single bonds, are free to have any kind of values. In such case, the overall conformation of the peptide, the backbone conformation of the peptide, will be primarily controlled by these 3 torsional angles alone, nothing more. Now, if I look at the distributions of these torsional angles, phi, psi, and omega, as is found in proteins whose structures have been determined experimentally, and those 3 round histograms, they give you an idea. What you notice that in case of phi and psi, the distribution is somewhat spread but is not uniform. If I can look out here, phi is rather concentrated in the -60 region but comes all the way from -60 to nearly -180. Psi seems to have 2 places which is rather popular, one around between 0 to -60 and the other one say between 120 to 180. Omega, on the other hand, that is the peptide torsion angle, is rather concentrated, very highly concentrated around the 180-degree value. And this, of course, our chemistry tells us that the peptide bond is rigid, it is not a pure single bond, and it is mostly in the trans conformation, which would correspond to a torsional angle of 180. So this means, therefore, that much of the variability of the peptide protein backbone is controlled by the phi and the psi angle, and even they are not uniformly spread about in around the -180 to +180 conformational space. Even they have certain preferences. If I plot the phi angle and the psi angle one against the other, so to summarize what I say, that the bond lengths and the bond angles are nearly constant to standard values as defined by the chemistry of the systems. The omega torsion angle is also nearly constant around 180 degrees. This we know because the peptide bond is trans. So almost the entire variation of conformation in peptides and proteins comes due to the variations of the phi and the psi torsion angles. And the variations of the phi and psi is what we need to study to find out how the protein conformation can take a particular conformation or how it can change from one conformation to another. Now, in this figure, what I did is that I took a very large number of proteins, about 90,000 proteins, and from there I extracted the phi and the psi angles for the individual amino acids. As you can see, there are more than 13 million amino acids have been taken, and for each phi and psi a little dot has been made in this. So there are 13 million dots in this figure, and you see the variation of the phi and psi torsion angles found in about 90,000 proteins. It's a very large number. Now, this would give us the total variation more or less, and you can see one thing very clearly, that this variation is not uniform. It is concentrated in certain places, and in certain other places it's much less. Now, why is it so? The answer to this question was the one which was first worked out by G. N. Ramachandran and colleagues. So let me go back now and tell what did they do to explain the nature of this figure. Of course, there has to be a beginning when one goes about, and so let us do it the way Ramachandran and colleagues did it. So what they did, they considered a very simple amino acid peptide analog. It was not a very large protein or anything. So at the top of the figure, you see the molecule which they considered. So this is acetyl alanyl methylamide, okay, or something which they call it the alanine dipeptide. It's a very simple molecule, and you have the phi, the psi, and the omega torsion defined in this. There are two omegas, of course, one at the beginning, one at the end, and the central phi and psi. Now, they also looked at the bond lengths and the bond angles of peptides, which are found at that point of time in several crystal structures. And there are, of course, certain small variations here and there, but the average values which they calculated are given for the bond angles on the left bottom and for the bond angles on the right bottom of this figure. Now, think about it. This alanine dipeptide, when it changes conformation, different atoms can come close to each other or go far away, right? Now, they looked at the conformations of many such amino acids and found out what are the smallest distance between a pair of atoms which are not directly bonded to each other, and they calculated. What they found that most of the time there is a certain normal limit of the smallest distance, but few exceptions are there. So they tabulated that. So on the top table you have the normal limits. These are the smallest distance by which a pair of atoms which are not bonded to each other, they can approach each other, while at the bottom are the extreme limits, that in few cases when the normal limits are violated, but nothing ever violates the extreme limit. Now, given this pair of tables, what they did is that they considered the alanine dipeptide, they changed its phi and psi angles, and of course this is in internal coordinate space. They converted that into external coordinate space, and they found out that if the distances between all pairs of atoms which are not bonded with each other, that must be within the normal, or in some cases within the extreme limit. And they found that every which possible values of phi and psi angles are not allowed. So if we just stick to the normal limits, then the regions in this figure which are shaded in dark color, only those are allowed, the rest are not. If we relax the criteria a little bit and go up to the extreme limits, then the additional regions which are shaded in gray, they become allowed. Now this was one of the first instances of an complete mapping of the entire conformational space of an amino acid residue, right, and obtained entirely computationally. Now how good or how bad is this? To see this, what I did is that I just superimposed the figure which they obtained from calculations with the data which I showed you before, that which has been collected from experimental data. Now as we can see, there is a reasonable prediction, but not very good. Maybe the left side of the figure, more or less everything comes within the predicted, at least within the extreme limit predicted region. But on the right side of the figure, we see a lot of points which are clearly outside the allowed regions. What does that mean? Were they wrong? Or there is something else going on out there? Now, even the answer was worked out by Ramakrishnan, and what they found out is that one of these amino acids, and this one is glycine, which does not have the C beta atom or anything like that. It's just the peptide backbone. Now, any interactions which the alanine dipeptide does with the C beta atom is now missing when it comes to glycine. So glycine should clearly have a larger allowed region. So they calculated the phi psi map for glycine, and they obtained something like this. So the figure on the left shows the glycyl Ramachandran map. Now what again, the dark regions are within the normal limits, while the gray regions are in the extreme limits. Now if I now take from my experimental data the 5' pairs of only the glycine residues, I can see perfect agreement. So whatever they had theoretically calculated perfectly matches, almost perfectly matches, let's put it that way, whatever they have obtained, what people have obtained experimentally. So some of the discrepancies as we had in the previous figure is obviously due to glycine. What happens if I get rid of all the glycines? So here is the experimental data shown for only for the non-glycine amino acids. Again, now I see that the agreement is far better. But again, at least towards the right side of the plot, I see quite a lot of points which have crossed out of the allowed regions. Now, this cannot be explained by the C beta atom clearly. There must be something else out there. What can it be? One of the reasons is that to a large extent is because of errors in experimentation. But there are other reasons as well, and which one needs to appreciate. Now, please understand one thing. The entire map, the way they have calculated, is based on certain assumptions. What are these assumptions? That all the bond lengths and all the bond angles are exactly the values which they chose, right? And this need not be the case. Say for example, if in the bond angle which they use around the C alpha atom was 115 degrees, and that's what gave that plot. If you make that 109 degrees, that is the tetrahedral angle, then you see that the map changes significantly and it becomes actually more restrictive. Now, different bond angles, bond lengths can slightly change, which would change the contours of this map. Then the omega torsion angle was strictly chosen to be trans. Now, that need not be so. About 1% of the time, and for a large number like 13 million, 1% is a very large number, you find that the omega torsion angle is not trans. It can even be cis, that is about 0 degrees, or can have different values in between. Now let us see what happens, for example, if the omega torsion angle is flipped. And what you see on the left is the Ramachandran map where the omega torsion angle is set to 0, something we call a cis peptide. And then what I show on the right is that I extracted from the data all of those examples where the peptide was cis. And when I put them on top, again I see that the calculated map very well predicts the experimental data. But again, few points here and there. So our current understanding is that whenever an amino acid moves out of the allowed region of the Ramachandran map, we first suspect that there is an error in the determination of the structure. If there is an error, there is an error. But if there is no error, then the answer is that there is something very interesting chemistry going on, something which is changing the bond lengths, the bond angles, and or the omega torsion, those things which have been assumed to be constant by the original calculation. Okay, one can measure that, one can recalculate the map, one can get a different kind of fit and all that. But generally, almost one is sure that there is some interesting chemistry is going on if it is not wrong. So the current status of the situation is this. The Ramachandran map, as I show around here, has become a standard tool for experimental structure determination people to find out whether whatever they have done correctly or not. So whenever a structure is determined, you find out all the 5' pairs, superimpose that on the Ramachandran map, and look how many of them are in the allowed region, how many of them are not in an allowed region. For those which are not in an allowed region, you go back again to your structure and you see whether you have correctly modeled it. If you have made a mistake, correct it. In spite of that, when you are absolutely sure that whatever you have done is correct and you are still having something disallowed, look again, some very interesting chemistry must be going on, because otherwise this kind of rare conformation would not be observed. So overall, this approach has made a tremendous impact in structural biology and is now standard operating procedure for every structural biologist to do a Ramachandran analysis whenever a protein structure is determined. So summarizing again, so the Ramachandran map is useful to locate residues in unusual conformations, and these unusual conformations may be due to errors in structure refinement, which is most of the time, but many times they also indicate rare special interactions. One example I'm just putting in is metal binding, but there can be other examples as well. And therefore, it points the eye of the scientist to where interesting science exists. So when you have thousands of residues have determined, this map very quickly tells you maybe there are one or two residues where something very unusual is going on for you to analyze and interpret. Thank you very much.